Hi, and welcome to day 8 of the advent of compiler optimizations. We're going to be looking at loops today, and in fact, we're going to look at a loop that inspired the very creation of Compiler Explorer. So, sometime in the early 2010s, I was working for a trading company, and the received wisdom at the time was that we couldn't use C++11's new range fors because it might be slower. Performance is really important in the trading industry, and we had just been bitten by a similar issue in Java, where Java range for equivalence created some amount of garbage, and that wasn't okay. And so we were a little sensitive to it. But I was adamant that we could use range fors. And so I hacked up a little script, and that script showed on one side an editor view, a VI terminal, and on the other side I was running in a loop a compiler with piping it through C++ fields and some greps and whatever. And every time you edited the code, of course, the continual running compiler on the left-hand side would update, and I was able to show the assembly code that was generated by a range for was largely equivalent to the normal loop. But we're going to try and reproduce that now in Compiler Explorer and talk about it. So let's create that same program. So we're going to just loop over and return the sum. So I'm going to use integers here, and we're going to say sum. I'm going to take a const stud vector of int vec. And then I'm going to write this the old school way, first of all, which is to say for stud size t equals 0. Sorry, I need to give it a name, don't I? Index equals 0. Index is not equal to vec.size plus index. I still use plus. I kind of vaguely prefer it. And then let's just try and get the indentation somewhat right. Someone should fix that. Now we're going to say total plus equals vec at index, and obviously we'll need a total variable, and then return total up here, and up here we're going to say int total equals 0, or let's just do that. And let's again fix the indent. What does the compiler do for this? We're on O2. Okay, so it's compiled. First of all, we're going to have to talk a little bit about how vectors work. So you probably know that a vector has some data in it and it has a size, but the way that it's stored internally, at least inside both the Clang and GCC implementation, is that 3 pointers live inside the vector. The first one is a pointer to the beginning of the allocated storage. The second pointer is a pointer to just past the end of the last valid element in that vector. And then the third pointer points to the end of the storage that has been allocated. So sometimes vectors allocate more memory than you're actually using, which means that they can grow without having to move things around. So the first pointer is the begin, then we've got like the end pointer, and then there's a sort of magical capacity pointer at the end. But they're all pointers. This is interesting because now we can look at the assembly code and understand what's going on. So RDI is the first register. It is a reference, which is to say behind the scenes it's exactly the same as a pointer, to the vector. So the first 2 instructions here are reading the 2 pointers out of the vector itself. So we have a reference to the vector, and we're reading the first pointer in that reference and the second pointer in that reference, which is to say the begin and the end pointers. Rax is begin, RCX is end. Now, if the subtraction is 0, then we know that there are no elements at all in the array, and the compiler has generated a quick escape here. It jumps if equal, which is to say if it's equal to 0 after a subtraction, to L4, which returns 0. Otherwise, we add RCX back to RAX, rather bizarrely, and then we set our total to 0. You can see Compiler Explorer is highlighting this as being total on the left-hand side, where it was when I was moving my mouse. So the strange thing that happened at the beginning here is it's sort of computing size. We're asking for vec.size, but as you might have realized, the size isn't actually stored inside the vector. In order to compute the size that we asked for over here, it subtracts the end from the begin, and then it sort of adds it back in again to find the end pointer, which is sort of unusual, and that's mainly because x86 likes to throw away one of the operands when you do a subtract or similar. So it's kind of undone it here. And then it loops around somewhat sensibly, counting up by the begin pointer. So it's sort of rewritten this loop, even though we've done it in terms of an index. It is moving a pointer forward by 4 bytes each time to read each element of the array, adding them to the running total of EDX, and then finally returning EDX in EAX after it's finished looping. Now, interestingly, and I've literally just discovered this while filming, if I change the not equals that I've done over here to less than, the compiler does something quite interesting. Over on the right-hand side now, you'll see that instead of just walking the pointer, it now is, in fact, moving the index forward each time. I'm not quite sure why it decides to do it this way, but we can see now that the size call itself has actually occurred. We are subtracting the two values, we're still jumping if they're equal to 0, but then we're shifting right by 2, which is to say we're dividing by 4, because those pointers are 4 bytes for each integer. So in order to get size into RCX, we have to divide by 4. And now we're counting up in ones. We're adding using the cool memory operand that the x86 supports. So we're using RSI as the base. RSI is begin, we saw at the top here. And then racks times 4 means racks many bytes times 4. So for each element indexed by racks, we're multiplying by 4. Then we're adding racks with 1 and we're comparing it with the size, and we're jumping if it's below. So here now it is checking to see if it's below rather than not equal, and that has seemed to have triggered all sorts of other bits of code in here that are less optimal. I'm not quite sure why the compiler has not worked out that it doesn't have to worry about this. Perhaps there's some kind of overflow if vec.size was no, because vec.size is a size D. I don't know. If you know, let me know. Now, the intention of this, of course, was to show that it's better to use range base 4. So let's change it to use range base 4, and a lot of this stuff will go away. Let's rewrite. So for auto lm in vec, total plus equals lm, get rid of all of this. And then what does our compiler generate? It generates the lovely code that we were expecting again. So there is no subtraction and comparison. There is a comparison actually. There's no subtraction though. It's not a comparison is a subtraction, I know, but the compiler is just generating sensible straight line code that is actually more optimal than the less than case that I would have otherwise naturally written. So the compiler has your back here. Just write a range for, or better still, use something like std accumulate. Let's just paste in my, whoops, I've got the wrong thing. There we go. And std accumulate, which I'll let you see by actually putting the mouse down there or pressing enter there. Just returning std accumulate does exactly the same thing. So it's maybe more readable to write std accumulate. You would just probably call it directly in this instance, but it generates the same assembly code. And for those who are going, oh my gosh, it's not generating vectorization, I'm deliberately leaving that till later on in the series, so please don't fret. We will cover it later. So the point stands, use range base 4s wherever you can. They're better than looping individually. They're less error prone, and apparently they will generate much better code under some circumstances. So something I learned today while filming. I will hopefully see you tomorrow.